As we begin our study of derivatives and differentiable functions, the absolute value function makes a particularly interesting example, because it's fairly simple and a function that you probably have some experience with, but it's continuous and not differentiable. This means that it's continuous on its entire domain, but it has at least one point where it fails to be differentiable. Let's see why that is. We'll begin by justifying the continuity of the absolute value function. Here is its graph, which certainly passes our intuition since it has no holes and no jumps. To be sure of the continuity, it would help to make sure that we understand exactly how the absolute value function is defined. And here is its definition as a piecewise function. The absolute value of x is simply x when x is at least 0, and the absolute value function is negative x if x is less than 0, since if x is less than 0, the absolute value function will have to hit it with another negative in order to make it positive. So if we consider the continuity of this function at any point with an x value less than 0, that would look something like this. Here's a point to the left of 0. Then approaching from the left and approaching from the right would just have our function behaving like this. Negative x, because we're talking about where x is less than 0. And every polynomial is continuous. Negative x is just a simple polynomial. So certainly, if x is less than 0, well, at all those places, the absolute value function will be continuous. Similarly, if x is greater than 0, that would look something like this. Then approaching from the left and approaching from the right has our function behaving the same way, which is just as x. X, again, is a polynomial, which is certainly continuous. So the absolute value function is continuous for all x less than 0 and for all x greater than 0. The only point that deserves special attention is where x equals 0. Because right here, the behavior of the function to the left is different from the behavior from the right. However, we can fairly easily show that the absolute value function is indeed continuous even at this point x equals 0. To do that, recall the definition of continuity. In order to show the function is continuous at x equals 0, we'll need to show that the limit of the absolute value function as x approaches 0 from the left is the same as from the right, which is the same as the value of the absolute value function at x equals 0. So let's begin this process by considering the limit of the absolute value of x as x approaches 0 from the left. In this situation, since x is approaching 0 from the left, all of the x values are negative, so the absolute value of x will be negative x in order to flip it and make it positive. So this is the same as the limit as x approaches 0 from the left of negative x. And then certainly we could just plug 0 in to find that this limit is equal to 0. And a similar thing is true for x approaching 0 from the right. From the right, since all the x values are positive, the absolute value of x is just x. And so this limit is the same as the limit of x approaching 0 from the right, or excuse me, as x approaches 0 from the right, the limit of x, because absolute value of x is just x when x is positive. Again, we could now certainly plug in 0, since we know that x is continuous, and this will then be equal to 0. And furthermore, what is the value of the absolute value function at x equals 0? Well, that would just be 0. So we see the absolute value function's limit from the left of 0 equals the limit from the right of 0, which equals the value of the function at 0. They all happen to equal 0. Now we've finished justifying the fact that the absolute value function is continuous on its entire domain. I'll move our work off to the side to make some room to show that this function is not differentiable. It is differentiable at most of its points. If x is less than 0, the derivative would just be -1, and if x is greater than 0, the derivative would just be +1. I'll leave it to you to verify that. I want to spend the rest of the lesson focusing on the non-differentiability of the absolute value function at x equals 0. It's right here where the function fails to be differentiable. I hope you can see why the function is not differentiable at x equals 0 intuitively from the graph, because what we see is that the slope is negative from the left, but it's positive from the right. So certainly the limit of the slopes from the left and the right could not be equal, and so the derivative there will not exist. This is what we call a corner, where the derivative from the left doesn't equal the derivative from the right. But just to show that this does in fact not exist, this derivative, let's make sure we recall the definition of a function being differentiable at x equals c. If it's differentiable at x equals c, that would mean that the two-sided limit as x approaches c of f of x minus f of c over x minus c exists. And remember, this limit expression is just the definition of the derivative. So what makes a function differentiable at x equals c? Well, it's if the derivative at c exists. To show that this limit doesn't exist, we'll evaluate the one-sided limits and show that they differ. One's -1, the other one is +1, which will show us that the two-sided limit defining the derivative can't exist, since the one-sided limits are different. So we begin by just taking this definition and applying it to our situation. We're looking at x approaching 0. We'll start off with approaching 0 from the left. And again, it makes sense to split this up into the individual directions because the behavior of the absolute value function differs depending on if we are to the left of 0 or to the right of 0. So here is this expression from the derivative definition. We have our function, absolute value of x, minus our function evaluated at the point in question, evaluated at 0, and then divide by our variable x minus the point in question. Again, that is 0 in this case. Now, since x is approaching 0 from the left, x is negative, and so absolute value of x, as we've discussed, is -x. So this whole numerator is just -x minus 0. In the denominator, we have x minus 0, which is just x. So this is -x divided by x. As we expect, this is -1. A nearly identical procedure shows us that the slope from the right is equal to +1. In this situation, the absolute value of x is just equal to x, because with x approaching 0 from the right, all of the x's are positive. So instead of -x over x, this just becomes x over x, which is +1. Then, since the slope from the left is -1, which is different from the slope from the right, which is +1, the derivative doesn't exist. This two-sided limit doesn't exist, so the absolute value of x is not differentiable at 0. And again, this situation is what we call a corner because the slopes from the left and right are different. So that's an explanation of why the absolute value function is continuous but is not differentiable. Hope this was a helpful explanation of these definitions applied to an example. Let me know in the comments if you've got any questions or video requests.
Head in the clouds like a little balloon, scaling the stratosphere.